All right, hello. We are here on the x86-64 enrichment lecture for the Cryptographic Systems course, CS 540 Cybersecurity. What I wanted to show today is a little bit more about assembly language. And assembly language is the thing one below C, a level of abstraction. So we have high-level languages. um, I guess Python's not necessarily that high level compared to something like maybe MATLAB. Um, Below Python, we have sort of the implementation languages for Python, which is generally C, and um, sometimes Python. I have Python 3 here, which is written in C. Um, but there exists PyPy, which is written in Python as well. Below the level of C, it is not necessarily the case that there is a physical piece of hardware anywhere that C code is running on directly, right? It has to get translated down further. And below C level, there's the level of assembly. And assembly corresponds to things that exist in the physical chip. An assembly instruction is something that corresponds to circuitry. Now, there are levels below assembly. Usually we get into things, say, like machine code or binaries, things like that. It is still a human-readable format. People wrote code in assembly for years, and many people still wrote code in assembly, though probably less than they used to, as C has become more mature and as Rust has come on to the market. Um, Nevertheless, there are some compelling reasons to work in assembly as well as the C programming language, and I'm going to give one example of them. So this is sort of all motivated um, by one assignment we had, um, the macros assignment. And in the macros assignment, I provide a reference solution that is written in assembly code. I'm going to pull that up on the screen, but in order to do that, I'm going to go through some of our process to do that again. I'm currently looking at a Linux terminal. This is a Linux terminal running inside Windows system for Linux. But it is Linux nevertheless. So I have Linux commands like ls, pwd, and I don't actually remember if those are Windows commands. I do have a Podman installation on Windows, or perhaps I don't. Oh, no, I do. Okay. Podman help. Or I guess I don't know if it's Podman or Podman. Doesn't matter. I also have the container file from the C89 and 99 lecture. So this is the development environment used for that lecture. I'm going to go ahead and bring that online. And let's see if I remember the commands. I always type built instead of build. It is quite goofy. C89 99 dot enter. That looks like it's working. And then we are going to podman run t vim, and I'm going to create something called, I guess I don't really want to call it x86-64. We'll call it 2 days.c. Adjusting. Okay. 2 days.c. Okay. Surely this will work, right? Vim did not resolve to an alias. Shame. Oh, is there Vim on that thing? Oh, I have to say C89. Okay. There we go. And this pulls up a C file. And I want to now split the screen so that I can look at two things at the same time. And I think the way I do that is Control W followed by S. Did I do it wrong? Oh, I have to escape. WS. I don't know what I'm doing. Okay. I'm not in the window, right? I seem to have broken my window. Nothing's working. Don't know what would have caused this. Can I... Mouse is working. But I can't use any keyboard commands. Escape doesn't work. Colon doesn't work. Control-C and Control-D don't work. Those are the usual suspects. Let's see if we can find our way home. Let's see. Oddman Peas. It's currently running. Oddman. I think it's kill. That's F4. Container already exists. Stop. More than one result for container. Oddman. Exec IT. Bin bash inside boring beaver. So, I don't actually know what I did to my container. I'm going to try and get back in. The container's currently running. Vim is in it. I don't know what's wrong with Vim. I'm going to try and use the exec command, which runs a command inside an existing container, and I'm going to try and get inside the container with bash instead of Vim. There we have it. And it doesn't look like... Does not look like Vim is running, so I'm going to turn this off. Okay. Oh, that's interesting. It was holding the window open. Okay. So from here, we will once again try to Oddman Peas. Okay. There is some way I can restart a running container. It is looking up Podman Peas A. Podman start. Which one of these? 3 minutes ago. Okay. F43. Podman exec IT 43 bin bash. Workable. Okay. All right. Podman. It's always a pleasure to work with, and I learn more every time I work with it. Okay. So what we were going to do is we were going to talk about assembly programming. And in order to talk about assembly programming, I wanted to demonstrate a bit of assembly code we have. The way I'm going to do that is I was going to grab a file from GitHub and look at it. Usually the way I do that is with curl or wget, neither of which is installed. So I can probably just grab one of those with apt. Curl is a command that grabs a file at a URL and brings a local copy onto my device. I'm going to cheat a little bit and copy paste something in from outside of the terminal. Am I? Can I even do that? There we go. Typing is annoying, but that's okay. This is the file. Let's save it. So it's called tester.c. I'm going to specify the output, and I'm going to call it... Ooh. No, before I do that, there's some way to reset the command line. I don't remember what it is. I just switched over from Python a moment ago. I'm going to switch to my home directory. I'm going to curl. I'm going to output that to tester.c. I am going to vim tester.c. And I am going to split the command line. Or split vim. Goodness me. Going to make one of them a terminal. No, I'm not. I'm going to make one of them a terminal. Okay. get one of these open, turn one of them into a terminal, close that, keep the terminal. Very good. Okay, so what's going on here? Let's see, Control W, W, that changes me. All right, so we have this testing script here, and it has some interesting things in it that we've probably not seen before. The solution the solution I came up with was to a specific problem. I wanted to give you some C code that tested your functions, and I didn't want to give you the answers, right? And so I did give you the answers, but I gave them to you in a way that you would have to learn something anyways. And that thing you would have to learn is what assembly is, and this is a super cool, fun thing to learn. I'm not going to worry too much about these first couple ones here. Wonder how many lines that is. Kind of want to delete. It's not 20, is it? 15? Okay, so let's look at this monstrosity here. Something much more interesting than perhaps the files that had a large amount of assembly in them is this rotate instruction right here. If you have tried to write a rotate instruction, which you should do for the homework, you'll probably notice that it's kind of annoying, especially because I've requested the use of bitwise operations, right? There's not sort of an immediate bitwise operation that does a rotate. But the reference solution right here, it does a rotate in a single line with a single function call, we could call it, right? And it's not really a function. It's actually an instruction, which is this more basic notion of a thing that exists at a lower level in the device. So what's going on here is I have a function. It is a C language function. But the only thing inside the C language function is ASM. And ASM, what if I can look it up? Oh, the system's been minimized. Okay. ASM stands for assembly, and assembly is the stuff that C code is written into. I'm going to start cleaning up main a little bit here to have less gunk when we actually compile this thing and start to look at it. But that is one instruction that executes in one clock cycle. So if you have a 3 gigahertz processor, that's 3, whatever giga is, it's like 10 to the 9th. That sounds right. You do 10 to the 9th of those a second. Oh, it's probably 2 to the 30th, not 10 to the 9th. I could be wrong. And so, like, I can do a lot of rotates per second, right? And I can do many more rotates per second than I can do Python multiplies, where I do 2 multiplies and an addition and do a modulo and all of this other stuff that it would take to synthesize the rotate operation. So this is very fast. It's very cool. It is the thing that is faster than macros, actually. And I'll encourage you to play around with this a little bit. But let's take a look at it. I want to delete some number of lines. I don't know. Oh, that's not what I meant to do. I probably want to keep the variables for now. Let's see, probably delete 10 lines. Probably do another 10. Ooh, I'm going to do 8. I'm not very good at estimating lines yet. Okay. So here is a rotate, and none of that stuff's usable because I didn't actually initialize the variables. Let's delete everything. Okay, 5D. Okay. Let's begin, actually. We have a single int main with an assembly instruction in it. Let's go ahead and save this code. Oh, I don't want an X, I want a W, because I want to keep the window open. Okay. So I've compiled the code. Let's make sure that I haven't compiled the code. I've saved the code. We're going to open the code. We have unsigned rotate operator. Okay. And then I'm going to compile the code. We can run a.out. And this is all well and good. It doesn't do anything. We can check the return value of a.out. Like so. You've done this before. We can provide the it's capital S flag to GCC. Press enter. I'm going to type ls, which is going to list the files in the directory. I have the executable I created. I have tester.c, which I wrote and is open in my Vim window. Then I also have something called tester.s. Let's see what that is. This is sh, not bash, and it is a lot less fun. Okay, so there's a bunch of stuff here, and I can't scroll because I'm in sh. So let's go ahead and open a Vim. Tester.s. Okay. Is that everything? Okay. There's a whole bunch of code here. And the takeaway I would like you to have is let's look at one specific line. I'm going to line it up at the top of my screen. Am I clever enough to do this? I'm not like the best person in the world at counting lines of text. So what's going on here? At the top of my screen on the left side, I have a .s file. It is an assembly listing, and it lists the instructions that GCC tells the computer to run. It is not quite an executable, right? It's not the same thing as a.out, but it is a lower level representation. In the case of GCC, this is for us. This is for us to know what the assembly looks like that the computer is being directed to do. But nevertheless, GCC can tell us what assembly commands are being used. On the right-hand side of the screen, we have tester.c, which contains one line of code that says return 0, and then a function declaration that is never used. There's not a lot of code over there. And I want to point out there is a large amount of code on the left side of the screen. And some of it is more useful than others. Let's just take a look at this file and inspect it a little bit. So at the beginning, we have a bunch of dot prefix things. These, provide diagnostic information about the assembly listing, right? So we see what file it comes from. This notes that it is a text file. There is a variable, a global variable named rotate that is of type function, which is specified here, right? Then we have the definition of rotate. This perhaps should at some level come as a shock to us that I wrote a function that contains a single assembly instruction. We claimed that the assembly instruction was the most fundamental or basic thing that a function could be. And there is a large number of other things going on in here. There's a bunch of notes, something that notes we're at the start of I'm assuming proc is procedure. I guess it could be process, but I think it's procedure. We have an end branch 64. That 64 is the 64 in the x86-64 name of the command line. We have a push Q on an RPB. RBP is the name of a register. A register is a piece of hardware that corresponds to a variable. It can store data and information. There is a finite number of them, which is quite different in Python and in fact in C and in basically every programming language I'm aware of, right? You can have as many variables as there are names for, and there's an infinite number of names, because usually you don't have a limit on variable name length. There's a large number of characters, right? So there's a potentially infinite number of variable names. Not so in assembly. The assembly can only refer to a certain number of registers, and it can only perform certain operations on those registers, right? RPB is one such. And the push command pushes a value onto that register. I believe this is something called the stack pointer. And the stack pointer how do I want to do this? When we call a function, there is a stack, and the top of the stack is, I think, where our BP is pointing. So it's pointing at some memory location, and we'll call that memory location, we'll call it x-decimal 100, for lack of a better word. Going down to lower memory locations, and we usually drop by 4 at a time. Why do we drop by 4? Well, we probably have 32-bit words. There are 4 characters of the minimal size in a word of size 32. Perhaps this is 64-bit code, because we saw that end branch 64. The R prefix on a register denotes it 64-bit. So perhaps this is moving by 8 bits at a time. 8 less than 100 is 98 hexadecimal. So perhaps down here you have something like, I don't know, maybe the 0 that's going to be returned by main. When a function is called, it starts pushing things onto the stack. And so something gets pushed onto the stack. I'm assuming the value of a register. The stack increases to begin at 104. The RBP points there. And this takes on some value, which we will imagine is perhaps 7. I don't know. I don't know what value is getting pushed on there, right? And that's super fun. The next thing that happens, what am I typing? Oh, okay. So we push something onto a certain memory location. We move an RSP, and I suspect it's more likely that the RSP is the stack pointer than the RBP. Let's see. RSP register is one of them points to the current stack frame, and one of them points to the top of the stack frame. I don't know enough about 64-bit operating systems to tell you the difference between those things. Anyways, these both point to wherever you're currently working in memory, that there isn't stuff saved yet. We're moving them between each other. Okay, we go down one more. Move Q. I bet Q is for quad word, so I think that's a 64-bit move, because that R denotes a 64-bit register, and this 64 thing denotes we're in 64. And I bet this L stands for long, which was the original name of the 32-bit words. They were long words because 16-bit words were double words, because 8-bit words were called words, are now called characters. So I think this is a 64-bit operation, and these L's are 32-bit operations. Why would these be 32-bit operations? I'm glad you asked. This is an unsigned value, and this unsigned value is of size 32 bits. We've verified it's of size 32 bits with the size of command, which notes that it is 4 times bigger than a character, and characters are known to be of size 8 because we can measure how big they are by adding 1 to them until they stop getting bigger, right? You can also double them in size until they stop getting bigger and use binary search. It's much faster. In fact, it's 255 divided by 8 times faster. Just 64, right? Could be wrong. No, it's 32. It's 32 times faster. So we have an unsigned integer here that is of size 4, or it is of size long. And so that's why we're using longs. Okay, what's going on here? 2 things are getting pulled out of the stack. What are these 2 things? Well, I can tell you. Before rotate is called, what should actually be present on the stack pointer, or on the stack rather, is the value A and the value B, because these are the function arguments, and the way function arguments are passed to functions is by throwing them onto the stack. So when we look at all this nonsense over here, what am I doing? Oh, I'm not in the mode I thought I was in. There we go. So when look at all this nonsense that takes place before the rotate call, which is right here. All of this is moving around the arguments to a function. Okay, that makes sense that could happen, right? But if the point of this is to do this more quickly, that's a large number of function calls. Each one of these is costing you one of your 3 to 4 billionths of a second, perhaps more. This is costing energy. Your device could be heating up. There's some lack of optimality here, right? But that's neither here nor there, right? What's going on? So we take EDI and ESI. We move them, and I think the second one is the destination, and it's easy enough to check. We can test in a moment. So we put these things onto the stack. We pop them off the stack onto EDX and EAX, and I'm just going to go ahead and say this code doesn't look particularly efficient to me. It looks like I'm taking EDI and moving it to EDX, and then I'm taking ESI and moving it to EAX. Then I'm moving EDX into ECX, and then I'm using EAX down here, right? So if I just track this code, right, I take -4 RBP, which is right here, EDI. If I simply put EDI right here, I would save this command, a single move, this command, and perhaps this command. No, I don't need that one. There is one special thing that I think is a little bit odd going on here. This thing called CL, that's some kind of special register, and it's just an alias for CX. But the rotate command only works if you call it on CL. And we can show ourselves that by trying to compile some code in a moment. Okay, so I claimed I only had one assembly command in my function, and that is demonstrably untrue, right? There's a large number of commands here. The rotate finally takes place. The rotate is into EAX. EAX is sort of like the most used register. You expect it to do things like contain the return value. We do a calculation into EAX. We do a rotate by the CL amount of the EAX value. We move EAX onto the stack frame. We move the stack frame onto EAX. Oh gosh, this is so inefficient. Presumably, I'm very, very bad at writing assembly code, and that's why this is so bad. Then we pop the stack pointer back off of after pushing it. And so we have restored our stack pointer, and then we call ret. I'm assuming what ret's going to do is it's going to grab the location here. And that location is going to be the memory address of return 0. So we actually can determine that at 0x90, nope, that is where return, that's the location of return 0. So we'll say that it points to return 0. Probably. I don't know, but it points to wherever rotate is called. Typing is challenging. Wherever rotate is called. Okay. So that's, I think, what's going on in rotate, and that's ludicrously complicated. Oh, I deleted the function name. It was called rotate, right? Let's go ahead and I want to get out of this Vim window. There we go. Let's go ahead and make some changes and see what happens. So come back over here. I think there's something that I can write static inline. And this causes the compiler, to my understanding, to no longer cause all of the sort of messy assembly code around doing whatever the stack frame is and around doing moving things in and out of various registers. Did I say that correctly? So I'm going to go ahead and try and run this with static inline, which is something I see in high performance code. It's not, I don't tend to write high performance code. I just thought it would be fun to try and write some for this class, so we're figuring it out as we go along. Static inline is going to, in some way, change the way that this function works. Guess I'll go ahead and call a rotate on something. Oh, it has different indentation. So nice. Okay, we're going to rotate. We'll do A5, probably, and we'll rotate it by 4. Okay. going to write that. I'm going to change. I'm going to compile with the S flag. I don't have a I have an unterminated comment. I kind of assumed when Vim told me to do things that way that it was the way I was supposed to do them. Oh, I see what I did wrong. I did not have the backslash, or that's a forward slash, right adjacent to the dot for a comment. Okay, tester.c, yes. Okay, Vim, tester.s. Let's see how this looks different, or how it looks differently. Oh, there's still a rotate there. Curses. No problem, I have a plan. The plan is, I'm going to manually inline this. Oh, did I save it? Cat tester.c. That's a static inline. Fair enough. Maybe I don't know what static inline does. Oh, let's see if I remember how to yank. Y, $, I mode, enter, paste. There we go. Right. And I'm gonna delete these. GCC tester.cs. Ooh! Oh, I did something silly. Okay, we'll delete that. GCC tester.c. Oh, I don't have my variables declared. I want there to be unsigned values. A, which is going to be equal to A5, and B is going to be equal to 4. Okay. Tester.c, code works. I can actually return this value to see what it is. A, GCC tester.c, a.out, echo. I'm getting 10 back. Is that what I thought I'd get? Probably. Seems fine. Seems low. That seems like a shift. Because I think OXA is 10. So I think the 5 is just vanishing. Regardless, let's look at the code. GCC tester.c \s, vim tester.s. Okay, what do we have here? No longer is there a rotate declaration. We only have main and main at function. 165, is that A5? Ends in 5, A is 10, decimal 10. In the 16th place, so that 165 is hex 95. We're pushing that onto our stack frame. We're also pushing the 4 onto the stack frame. Okay, we're moving things from literals onto the stack frame, and then for some reason we're moving them into EDX, EAX, then we're moving them from EDX into ECX. So the 4 here goes 4 off of the stack frame, then it goes into EDX, then it goes into ECX, then it's renamed into CL and used as the rotate amount applied to EAX. Then EAX is put onto the frame, popped back off the frame is popped, and we return the value. And for somehow that value is 10, right? So perhaps I didn't calculate my rotate correctly or something, right? Pretty cool. I think this would be a little bit cooler. Maybe we don't need any of this stuff at all. Maybe we delete all these lines. And what should we do in here? Well, initially we had return 0, but we don't even actually have to do that. I'm pretty sure the return value is in the EAX right here. And if the return value is in the EAX, all I have to do is do an assembly moval. I move a literal value, $0, into, I think it's denoted %EAX. Those lines don't seem to be terminated with anything, so I'll just close the paren right there. I have to semicolon terminate this because it's back in C now. And I'm going to go ahead and write that. Oh, I forgot to exit this over here. Okay, so we gcc tester.c a.out. I expect this to have a return value of 0. It does. What happens if I change this to 10? And I gcc tester.c. And I don't necessarily know that I think this will be 10. That's still 0. Why is that still 0? Well, int. I've told the C compiler I'm going to return an int. I bet the C compiler is putting a 0 in that return statement without me asking. And to prove it to you, I'm going to open tester.s, and I'm going to see what happens. So here we are in tester.s. We only have a main. We have an end branch. We have a push. We have a move. We move 10 into EAX. And then what do we do immediately after that? The compiler moves a 0 into EAX. So I'm still returning 0. Not to where I have a plan. Not the start of the line. I can tell the C compiler I don't want to return anything from main. Why don't I just do that? Write this code. Come back over here. Exit vim. gcc tester.c a.out. Echo. There's a 10 right there. This function, this main function, I've told GCC to not return anything. That directive for GCC to not to return anything is being overruled by the internal assembly. The internal assembly is causing a value to appear in the EAX location, which is expected to be the return value by the command line, right, and by anything else. The return value of that function, then, is being placed where you'd expect it to be. And because I've told the compiler to not return anything, it's not overwriting it. So it's just not returning anything at all in its view. And sneakily, I'm using an assembly command to subvert the GCC compiler. I thought this was pretty cool when I found this. It took me forever to find this thing. I think that's downright slick. That's just what I think. And so maybe we should write a rotate like this, right? What do you think? We put something inside EAX. Oh, one of the things I wanted to say, gcc tester.c. This doesn't draw any warnings, but I have advocated that we should use standard C89. And in C89, assembly isn't defined. You're supposed to use _ assembly. I'm pretty sure. gcc tester.c. I can't just press the up arrow and get this because the vim terminal is running sh instead of bash. So that's why I'm manually typing everything. And I'm sure there's a very, well, can I do this? Oh, by golly. That's uncommon. That's incredibly nice. Okay. We get the 10. Okay. I can move 10 into EAX. I was previously going to move 165 into EAX. So let's do that. Let's yank this. I remember how to yank things. Oh, I'm in insert mode. Yank the end of the line. Drop down. Insert. No, not insert mode. Paste. beginning of line, delete that, ren, end of line. There's got to be a way to add a new line. I don't know what it is. Insert mode, enter, close curly bracket. Okay, and then we go. I want to change this to a rotate roll. I have to put something in the CLI, or the CL. Rotate into CL. I have to do another one. Enter, escape, paste. No, yank, paste. Rid of these open lines. I don't know why I got them. Okay, I need to move a 4 into ECX. And then I need to do a rotate. For all I know, this will work. GCC tester.c. Ooh, bad value. CL cannot be used when making a pi object recompile with fpi. Sure. Relocation X. Can I just do this with regular? I haven't figured out my keybinds for visual block mode, so I have to do this line at a time. Ooh, it really doesn't like that. That's a shame. How did it work before? I don't recall what it looked like. I had a CL, right? Oh, I see. It's I'm a silly goose. This can't be a dollar sign. Percent. The percents and the dollars look identical to me. Or appear identically, I should say. Couldn't even tell the difference. Let's change these back to. It's humiliating to not know a fast way to do this in Vim. But we're learning together. Okay. Exit. Save. Tab over. GCC. Tester.c. Cut out. Echo. There's your 10. Okay. I guess I didn't. I expected the right rotate to loop around somehow. Oh, because that's what I thought it was doing. Whirl. Oh, let's try left. Surely that's rotate left, right? Oh, I forgot. I'm in Bash now. I can just press up and get things back. Okay. Oh, that's 80. That's 80. Not capturing the 65. Okay. C tester.c. S. Vim. Tester.s. What's going on here? This is some hijinks. Okay. Putting 165 in EAX. Removing 4 into ECX. I'm pretty sure that 4 is the same value as CL. We're putting into EAX. Really thought that was gonna roll. What happens if we add them? Add long EX. Get 169 out of this, I think. Okay, very good. So I can add things together, and that behaves as expected. Or what other operations I can do? I think there's different shifts. Escape and W. Control W, W. There we go. Okay, the rotate is doing the same thing as a shift. And that's a SHRL. I thought there was also a SARL. A left shift? I think this 165 just isn't working correctly. Okay. That also gives me a 10. Okay. So the thing that has to be happening here is these are differing with respect to the high-ordered bits. I'm going to comment these out. I'm going to use C++ style comments because I'm already breaking all the rules. That is getting a 165 in EAX. This gives me an undefined value in ECX. Okay. That gives me a 4 in ECX. I wonder if I'm doing something wrong with the 4. $82. 82 is half of 165. So that is doing a shift of 1, but it's not doing a full rotate. Let's turn this over into a rural. $82. Okay. Here's what I think's going on. I think I need to tell the compiler that these are unsigned values. Just going to call it A. And I'm going to switch to extended assembly. Do I have to? I'm just going to declare A as unsigned right there and take a look at it. Still 82. Okay. I'm wondering if the sign bit affects things. Oh, can I put a -1 in there? Ooh, forgot to press insert. I. -1. Read. That's interesting. It's treating them, I think. Oh. Let's do 4. Oh, gosh. I'm looking too many places at once. We write the 4, we tab over, compile. Right, okay. So, what has to be going on here? -4 is 4 less than 255, so that's 251. What I think that means is the 4's place. I should just binary print it, because it's easier than thinking about this. If I add 1 to -1, it becomes 0. And if I add 1 to 255, it becomes 0. That means if I add 4 to -4, it becomes 0. And there's no bits set. It's all 0 bits, and it'll show up as 0. If I take that -4, that 4's digit, and I move it over 1, that should change to this being the case where if I add half as much to it, so if I add 2 to it, it becomes 0. Which means I need to add 1 more to it than I add 255, which means I need to add 2 to 254, because 254 goes 255 and then 1. So in fact, that is a correct shift. It is a correct rotate. It is simply rotating at the level of an individual byte. Probably. What happens if I do 7? That's a 0. What happens if I do much larger value? I think this might be off by 32, so we'll do 30. Oops, 30. Save. There we go. Okay, what happened here? The return values are, I'm only getting the last 8 bits of a return value through the console, which means if I want to do a rotation to detect bits, I have to rotate all the way back around into those last 8 bits. If I rotated 32, I would have rotated all the way through the 32-bit word. So what I actually want to do is I want to do a small roar. I don't even know if that's a command. Ah, close. And this, whoa! Oh, gosh. How many do I think of those there are? There's 5L, D3L, okay. That's still a 0. Okay, so roar's not working. Roar S. I don't know if short's bound. Yeah, okay. So the smallest one, maybe W? Does roar word work? Ah, we tried. Ooh! These registers are wrong. It's supposed to be CI. Add register name CI as CL. Okay. What's going on here? I'm thinking a little too hard, and I'm just typing. Okay, so here's my theory. Why did it do that again? Probably because I'm mashing keys without thinking about it. So I have 1. I set the lowest order bit, so I have 1, 2, 3, 4, 5, 6, 7, 1. Okay. I move 10 into ECX, which is 1, 2, 3, 4. I have an 8's digit, no 4's digit, a 2's digit, 0 digit. Okay. I do a word rotate, size 10. So I take that 1 and I move it 10 forward. Now I'm guessing words are 16 wide. So if I move it 1 forward, that is a 1 followed by 15 zeros, but I move it 9 more than that. So I have a 1 followed by 6 zeros. 1, 2, 3, 4, 5, 6. That is the 1's digit, 2's digit, 4's digit, 8's digit, 16's digit, 32 digit, and 64's digit. RORW is a 16-bit rotate. I can only see the bottom 4 bits. Now I can only see the bottom 8 bits, which is why it's showing up as 16. To demonstrate I'm definitely seeing the bottom 4, put a larger number in here. And we get 192. So what is 192? Well, I started with all 1s set in the bottom 8 bits, and I rotated by 10. So those last 10 came in, and they had 6 zeros after them. So I have 1, 1, 1, 2, 3, 4, 5, 6. This one is the 64's place. That one is the 128's place. 128 plus 64 is 192. That's what I'm seeing with my rotate. What's kind of put in here? So I always think of I tab. I like A because it's alternating. We'll do A5, A5, just like we started with, and then we'll do some rotates. That is 105. and this is going to be something close to that. I'm learning something about Vim, but I'm not sure what it is. Escape, save, tab over. Okay. So I have turned on an alternating pattern of bits. A is 1010, 5 is 0101 within the 4 bits of a hexadecimal character, right? So I take those values, I move them around. If I move them around in odd number or even number, I get different values. I move them around 10 bits. I'm not going to manually figure out what that is right now, and I got 210, which is 45 less than 255. Yeah, figured it out. I moved them around a little bit more, and it fell exactly in half. And if I switch to 8, it will be some other, not that different. I really need to learn how Vim works. I'll get 165. Right. So that is that's assembly code. That's how it works. It's unbelievably cool. It's wicked fast. Let's just end by looking at what we finally ended up with. Tester.c.s, vim, tester.s. And you'll see we have a series of move and rotate instructions. There's a no op, which is returning void, I'm sure. And then we just return whatever's in EAX, which is actually the same thing that's in AX. E is the extended AX. So it is the long EAX, the same way RAX is the quad X register. This is the, I think 8 is like augmented, so that's the 16, and then there used to just be X, which was the 8-bit. And there you have some assembly code for you. It's ludicrously fun. I've been like doing nothing but screwing around with this for a few days. So hope you enjoyed just writing